cylinder there gives us the sync function here.
Sync here.
So we're getting the Fourier transform. What's going to be the pattern from this? So this is two cylinders.
And
So
a
this was
cosine
homework
function.
problem 1.
It's a
Sombrero and the cosine
It's a
function.
sombrero multiplied by a
Cosine
cosine.
function.
And
That's what
the
we
sine period of
Yeah.
the cosine is going to be determined by how close together these holes are.
Cosine function? Yeah. We won't be able to see the imaginary. Lights off.
I'm in the way.
Oh, yeah.
Now I'm not in the way. All right. Now, hold your applause. Isn't that dazzling? I mean, that's there
Exactly
is
the
That is pretty cool.
there is the cosine fringe pattern.
Oh,
wow.
Yeah.
You
That's
got to
really
get
cool.
close to see it. You can't stand in the
Sorry, I'm recording for people who
Well,
aren't able to
should
be with us today.
Oh, wow. You guys, so cycle through. You know, make sure everybody gets a chance to get close.
Oh, nice.
And, you know, take your time. I mean, we're not rushed for time. So what I'm gonna do now is open up a third hole that's twice as far apart and then cover the middle hole. So I'll have two holes that are, right now I got two holes that are 1/10 of an inch apart, then I'm gonna have two holes that are 2/10 of an inch apart. Your dynamic range of your sensor is not gonna be enough.
You
gotta see this.
Okay.
It
so
is.
now-
I did get it.
So what I'm gonna do.
Yeah, I got a good video of it.
Yeah.
With the magic of blue tape, is I'm gonna take this thing and I'm gonna open up
More holes?
a third hole,
Oh,
but now what I gotta do is cover up the middle one.
So we are getting the same thing we saw in our homework with two subs.
Well, they're further apart.
They're further apart.
we are blocking the first one.
What I need is a better piece of tape, but I think I can jury rig it enough.
Yep.
Okay,
Nope,
so now,
nope, nope.
well,
It's coming on.
it just has to block it.
Yep.
All right, so now I got two holes that are farther apart.
Right.
What's gonna do?
Farther apart.
It's gonna
Same size hole.
Same
but they're
size.
widen the
farther apart.
cosine function, the cosine.
White function's gonna.
It be more frequent, like there's gonna be more peaks for the.
No, it's 2 pi
It'd be-
epsilon x, right? So the epsilon is increasing. So
Yeah, so frequency would
the
be.
frequency will
That's
be
yeah.
So
The
we would
frequency
see
is
more
wider.
frequent-
wider.
Oh,
Yeah.
You're right.
Of course, now you have to remember what you saw before.
Oh, it is doubled.
It is double.
Yeah.
That's what I
When
was
you say
saying.
it, what is double?
The cosine frequency.
cosine
The
Cosine
frequency is
frequency
double,
double.
the period is half as big.
Right. Yeah.
Right. Yeah. Yeah. The frequency is doubled.
So, and think about what's happening. The stuff that's small over there, which is the hole compared to the separation, shows up big over here. So this gives you a tool to make measurements of stuff that's really small. You can measure the diameter of that hole by looking at its diffraction pattern. The smaller the hole, the bigger the pattern. The easier it is to measure. It's fainter, but so it gives you a very precise tool for measuring very small features. Okay? So the point is, what I'm seeing here is the Fourier transform of what I put there.
Okay.
And we haven't written the math down yet. It's really easy. It's in the write-up. And we're going to do it in class too. But right now, let's just say that's what it is. Okay? So what I'm going to do now, I got a bunch of different objects here. I got a letter E. I cut this out well before you guys were born. This thing is probably dates from 1983 when I did it.
Some of us are older than you think, Roger. Not that old though.
So what I'm getting here, and I should emphasize that I didn't, we're getting the squared magnitude.
Right.
Because it's, so the E has, horizontal lines, which give me a spread in the vertical direction.
Vertical direction.
It's got vertical lines, which give me a spread in the horizontal.
Right.
direction.
So there's my E. My Fourier transform, square magnitude of Fourier transform of E.
Yeah.
So now what I'm gonna do is go get a quadratic face. And this is, a lens is a quadratic face. So I got a different kind of thing.
Doesn't
I'll
look
show you
much
that too. But this is what's called a Fresnel zone plate. So the negatives parts are shaded black and the positive parts are transparent. So this is like a bitonal, a half-toned zone, quadratic phase.
What do you mean by tone?
Half-tone, it's got two levels. That's, again, one of your exercises is gonna be half-tone. So, now I'm gonna put this in. This is gonna be an approximation of a chirp. What's the Fourier transform of a chirp?
It's a.
So, okay, and it's windowed by a circle. So what we just did with stationary phase, we're gonna get a circle times a chirp. Okay? So, and then what I'm gonna do is put these two together.
Thumb and a chirp thumb.
Okay? So there's the quadratic phase.
There's another function, that will be.
And we're seeing the squared magnitude of the chirp
Wow, yeah.
Yeah.
times the window. So what you get is it's a uniform, finger quotes, brightness
That's nice.
times the quadratic phase,
More in circle as well.
times the square magnitude of the quadratic phase.
But the fact is,
Okay, everybody, well, don't let me rush you. Cycle through if you want to get close. We got time. This is my favorite thing. I love this stuff. This
Nate,
is,
you want me to hold it for you?
I got it. Yeah, okay. Just read it for.
the next one is gonna be actually worth taking a picture of. This is boring. But the next one is not boring. Remember, we did stationary
To
phase.
understand this quadratic phase, the
We're seeing the
circles-
squared magnitude of the quadratic phase times the aperture function. So,
my
if
question
I
is-
have a circle times a quadratic phase in the space domain, what I get is a circle times a negative quadratic phase in the frequency
Yep,
domain.
yep.
And I'm seeing the squared magnitude of that.
So, I mean, I believe these are the lines for quadratic phase. the
Don't,
inside.
don't worry about the details,
Okay.
just the,
Just look at it.
okay.
Need it all
And go ooh.
circular by
When you
some-
see the next one, then your questions will come in.
So.
Okay, everybody see it?
Yep.
So what I'm gonna show you next is I'm gonna take the E and sandwich it with the quadratic phase.
Okay.
So we'll
Okay.
get E times the quadratic phase, what are we gonna see here?
So there will be vertical lines and horizontal lines along with
That's the Fourier transform of the E, is
And
that,
then
Yeah.
Right.
but think stationary phase.
Okay.
So-
We're gonna add the E as well, I guess.
So here, I've got a circle times the
Will we get a
quadratic phase.
pattern of E's?
Pattern of
Now,
Pattern of these.
like straight lines, and then it. I'm not sure about it.
so here's my E, here's my quadratic phase, and what I'm gonna do is that.
Okay.
What are you gonna see here?
I guess an
E
E.
times that
E
quadratic
times.
phase.
E times the square magnitude of the quadratic phase.
So we get an E.
Just
So
an E.
this is the
just
We don't
illustration
get the
of the
original
stationary
version.
phase.
Remember? Stationary phase.
Right
Yeah.
there.
Uh-huh.
see the.
Super cool.
Wow. But I
Amazing.
haven't seen any.
Now you see two of them.
Yeah.
Because everything's real valued.
Uh-huh.
We don't have it, and so the Fourier transform has gotta be even.
oh,
The real part of the transform's gotta be even. The squared magnitude is even. So, it might be me that's in the, that's me. And now, while it's there, let me go move the E around, while you're watching.
Hold on, not yet.
Remove it first.
Ooh. Okay, I started recording it. So.
Are you rotating?
I'm just moving it, I'm just translating it relative.
But it is rotating.
Okay, so there's the illustration of stationary phase. Function times quadratic phase, Fourier transform is function times quadratic phase with the opposite sign. And then there's the constant phase, which we can't see anymore. Okay, everybody buy that?
Yep.
Yep.
All right.
He's kind of.
Would it be valuable to use a different object with the quadratic phase? I
You
don't know
can't
if
see
it
the.
would.
It should
that
be.
proper like
I've got a
pathways
triangle somewhere.
for the
What are you trying to capture, CJ?
Did you not do the
exactly. I don't know. He's just
It's a nice,
Well,
nice looking wall.
I don't, I'm looking for my triangle, I don't see it, it's probably here, but I have to find it. But I think, so everybody's comfortable with what that illustrates?
right?
You know, you understand the stationary phase? Okay, so now, let's just do, arguably the stuff we should have done first, which is, here I'm just gonna have a simple square. Okay, so that's a two-dimensional rectangle. What's its Fourier transform gonna be? A 2D sink. So, and then we're gonna see the squared matrix.
Sink times like sink.
Well, it's a sink in X and sink in Y, so it's a, yeah.
It should be
It'll
a
look like,
circular pattern of
it'll look
sink.
like a sombrero kind of, but
Sombrero kind of.
with bigger peaks, I think, right? Yeah. And falls off slower than a sombrero.
So there's the Fourier transform of the rectangle.
Yep, you can see.
So there's the squared magnitude of a two-dimensional sink. There's a sink square. Okay, and again, cycle through and don't let me rush you. We got plenty of time.
Cool.
Cool eats.
So, where we're headed is, then we're gonna put in an object that's got, we're gonna put in the Fourier transform an object encoded. And we're gonna see the Fourier transform of the Fourier transform, which means we're gonna see the object back. And that's the computer generated hologram. Okay? Again. And we've already done the circle, so I don't need to do that. I do have a halftone image, which I want to. Everybody see that?
Yep.
Okay. So, and I've got to keep track of these. So here is a two-dimensional comb function. So it's or grading. We could think of it that way, right?
Two-dimensional what?
Well, it's a
Oh,
comb
comb.
this
Oh,
way
yeah.
and a constant that way.
So isn't it acting like a
Line,
grading?
line delta.
So it's a great. I mean, that's what a comb is. That's
Comb
what a
is,
2D
right?
comb is. It's a
Yeah,
grade.
it's a